Today, we're finally going to look at our first simple machine, and we're going to look at levers, which there's a lot going on with levers. So today we'll just do a kind of an introduction, how to differentiate the type of levers, and then next class, we'll actually start doing some equations and solving some problems with them. For now, we'll just look at the basics. In its simplest form, a lever is a rigid bar that's allowed to rotate at some angle about a pivot point, and that pivot point we call the fulcrum. That might be a vocab word you're familiar with. Now, to connect back with what we were doing last week, we can calculate the mechanical advantage of a lever system. We have the ideal mechanical advantage and the actual mechanical advantage. Now, if I want to calculate the ideal mechanical advantage, that is the ratio of the distance traveled by the effort force to the distance traveled by the resistance force. And a way that you can remember that is the expression, I'm a deer. You can kind of see how that shows up. I'm a deer. And if I want to find the actual mechanical advantage, that's the ratio of the resistance force to the effort force. And an easy way to remember that is, am I free? Am I free? Am I free? Two little expressions that'll help you keep those two things straight in your mind. Now, looking at this lever, if I put my effort force on the left end, call that Fe, and my resistance force on the right end, and remember, we'll also call that the load. So I'm going to use resistance and load interchangeably as we go through this. Just know it's the same thing. Now, the actual mechanical advantage will be pretty easy to calculate here. We just use the ratio of the two forces. The ideal mechanical advantage, we have to look at what would happen if just one of those forces were acting. So if the effort force was acting independently, it would cause the lever to rotate about the fulcrum in a circle, like that. If the resistance force were to act independently, or if the load were able to act independently, it would cause the lever to rotate about the fulcrum in a much larger circle, right? And so we can look at the distance traveled by each of these forces as the ratio of the circumferences of these circles. So if I want to figure out the circumference of the big circle, we just need to figure out what's the radius to the resistance force from the fulcrum. And we will just call that R, we'll call it RL because it's the load, right? This is also FL. So that would be to the load, and then to the effort, that would be RE. That's the radius from the fulcrum to the effort force. And now for our ratio of the circumferences, circumference is 2 pi times the radius. So RE over 2 pi RL. And we can see here that this is going to simplify. The 2 pi's are going to cancel out. And so we can simply find the ideal mechanical advantage by determining the ratio of the distance of the effort force from the fulcrum to the distance of the load or the resistance force to the fulcrum. So this is the easier, you can just jump to this. You don't have to derive that every single time. But just how it connects with the original formula. But this is easier to use. So the actual mechanical advantage, we would just use the ratio of the forces. That's enough for us. Now, there are three different classes of levers, three different classes. And each one has a slightly different setup. So let's look at first class levers. This is what is going to come to mind when you think of a lever. This picture right here is a first class lever. So just a little quick sketch. We have our fulcrum in the middle. We've got the effort. We'll use the load. Okay, so all first class levers have the fulcrum between the effort and the load. And all first class levers will see that the effort and the resistance forces, or the load forces, act in the same direction. So in this case, they're both acting down, right? Act in the same direction. And there are three different situations that you'll see when you see a first class lever. So you could have it, I'll go ahead and just call these A, B, and C. The first situation, which is the least interesting, is when your fulcrum is right in the middle of your effort and your load. And if your fulcrum is right in the middle, that means the radius to the effort force is equal to the radius to the load. And in that situation, you have no mechanical advantage. You don't actually benefit from using a lever. You might as well just pick up the load. All this does, the only thing this does is it changes the direction of the force. Right? If you push down, it's going to cause the load to move up, but it won't change the magnitude of that force. And if we're looking at, say, equilibrium, right? Equilibrium means that the bar is not moving. That means that the forces would be balanced. So the effort force is equal to the load force. So that one, not super interesting. It just changes the direction. The next case that you can see is where the fulcrum is much closer to the load. And further away from the effort. So we can say that the radius to the effort is larger than the radius to the load. And in this situation, this is where you actually get a mechanical advantage that benefits you. It's going to increase the magnitude of your force. So you would have a mechanical advantage that is greater than 1. And so this decreases the effort force that is required to move the load. And so the effort force is going to be less than the load force, because by increasing the distance, you're minimizing the amount of effort you have to put in. And then the last situation, we'll squeeze this at the bottom, is when the effort force is closer to the fulcrum and the load is further away. So we have a radius to the effort that is less than the radius to the load. And in this situation, this means that we're going to have a mechanical advantage that's less than 1 because you don't get the benefit of having that distance. And so it's going to require an effort force that is greater than the load force. And it increases the distance traveled by the load. So say you want your load to swing really wide, then you would put your fulcrum closer to the effort. You would have to put in more effort, but the load is going to cover a greater distance. So in this situation, the effort force is going to have to be greater than the load force. Some examples of first-class levers would be a crowbar, or a seesaw. Something where you have the effort and the load on opposite sides of your pivot point of your fulcrum. So that's first-class levers. And then now we're going to look at second and third class levers. Now these two have some things in common. We'll talk about what they have in common first. For these two, the fulcrum is going to be located at one of the endpoints, or one end of the lever. Whereas with a first class lever, the fulcrum was somewhere in the middle. On a second class and third class lever, we'll have it to where the fulcrum is at one end, and then you have forces acting on one side of the fulcrum. And as you can see from the picture, I drew that intentionally that way, the effort and the load forces act in opposite directions. They have to. Okay, so now let's see how we can differentiate between the second and third class. So a second class lever, we'll draw this setup one more time. We have a fulcrum at the end. Now a second class lever has the effort at the other endpoint and the load somewhere in the middle. So we can say that the resistance or the load is located between the effort and the fulcrum. For a second class lever, that means that the radius to the effort force is always going to be greater than the radius to the load. And just like what we saw in the last situation with first class levers, if the radius to the effort force is larger than the radius to the load, then we're going to have a mechanical advantage that's greater than 1. Okay? One thing that you can do to manipulate second class levers is by moving the load closer to the fulcrum, you can increase the mechanical advantage of the system. So having the effort force and the load force farther apart, but still on the same side, that increases the mechanical advantage. Some examples of second class levers would be like a wheelbarrow, where you have the weight in front of you and you're lifting at one end, or a nutcracker, where the nut is in the middle between the wedge and the not like the wooden soldiers. You'll see it on the activity. And then lastly, we've got our third class lever. It's got the same basic setup as a second class lever, except this time the effort is in the middle and the load is at the end point. So we'll describe this by just saying the effort is between the load and the fulcrum. And again, just like with first class levers, where the radius to the effort force was less than the radius to the load, we'll have a mechanical advantage that's less than 1. So we're going to require a larger effort force to move the load. Now, some examples of third class levers would be tweezers or tongs, where you have the grip at the end, right? The load where your force is being transferred to is at the end. One that's less obvious would be a shovel. Your back hand on a shovel is stationary, so that's the fulcrum. Your effort is the hand in the middle that's pushing up, and then the load is whatever you're scooping with your shovel. So we've got an activity where you can see some different examples. You've got multiple opportunities to take it, and I'm pretty sure it'll tell you either the right answer or which questions you got right or wrong. But this is just our basic introduction to levers. We'll do some problems where we have to use the setup of the lever to calculate the ideal mechanical advantage, the actual mechanical advantage. We'll also look at the efficiency, right? Efficiency, same thing here, is eta. And we said that that was the actual mechanical advantage over the ideal mechanical advantage. Same equation applies here. Okay, so there's our basic introduction to levers. Go ahead and do the activity on Schoology. You have multiple chances, should be pretty easy, but it'll get you used to identifying which class of lever certain objects are, because it's not always super obvious.